Hello, today Aziz and I will present our work on safe locomotion navigation in partially observable environments with uneven terrain. Bipedal robots are becoming more capable as basic hardware and control challenges are being overcome. However, reasoning about safety at the task and motion planning levels has been largely underexplored in the field. We would like to make key steps towards guaranteeing safe locomotion in cluttered environments in the presence of humans or other dynamic obstacles by designing a framework that deals with the high dimensionality, nonlinearity, and under-actuation of these robots. We propose a hierarchical task and motion planning framework that incorporates safety guarantees at each level. At each walking step, a high-level temporal logic-based planner evaluates the robot and environment state and determines a safe action set to achieve the planner's navigation goals. To generate feasible motions, we have designed a low-level face-based planner. This planner consists of two subplanners. A keyframe decision maker that uses the current keyframe state and the high-level action set to determine the next keyframe state, or the state of the robot at the point of minimum satchel velocity at the next walking step, and a motion planner which generates a center of mass trajectory between the current and next keyframe state using a reduced order prismatic inverted pendulum model. Keyframe-based locomotion is inherently discrete and allows us to design a discrete high-level navigation planner. To guarantee high-level safety, we construct a reactive game between the robot and the environment using linear temporal logic synthesis. We generate LTL specifications that govern how the game is allowed to evolve. Within these specifications, we encode goal completion, collision avoidance, and locomotion safety properties. We use a discrete grid abstraction of the environment to model how the robot at a possibly adversarial obstacle may move through the environment. At each walking step, the robot must generate an action set for the motion planner to execute. This action set includes step length, step height, and heading angle change. We require a relatively fine discretization of the environment to deterministically model the robot's next state based on its current state and action. To avoid the computational burden of such a fine abstraction, we further divide our task planner into two layers: a navigation planner that operates on a coarse global discrete abstraction, and an action planner that operates on a fine local abstraction. We model static and dynamic obstacles in the coarse navigation planning layer, and encode collision avoidance and goal completion guarantees in LTL specifications. The robot must visit goal states infinitely often in the correct order. We combine the environment abstraction and safety and goal specifications to synthesize a planner which is then implemented as a finite state machine. For action planning synthesis, we model the fine local environment within each course cell. The planner generates an action set at each walking step and must guarantee the desired transition in the navigation game is achieved after several steps. Locomotion safety properties are specified to ensure only safe actions are chosen. We have designed our planner to operate in a partially observable environment. To reduce overly conservative behavior, we employ a belief abstraction to track the planner's belief of possible dynamic obstacle locations when the obstacle is out of sight. The planner is able to use this belief to guarantee which non-visible regions are obstacle-free. To generate the belief abstraction, we divide the environment into belief partitions. When the obstacle is out of sight, the planner's belief state is an index representing which regions the obstacle could be in. We must accurately model how this belief evolves as the obstacle remains out of sight to guarantee which cells are still obstacle-free. The dynamic obstacle may transition to any adjacent cell. If any adjacent cells are non-visible and the obstacle is not visible after its turn, then the belief state represents the set of regions containing these non-visible cells. Once the obstacle is not visible, the planner believes it could be in any non-visible cell represented by the belief state. Since the obstacle may transition to any adjacent cell, we can model which new belief regions the obstacle may have entered. Lastly, we can also model which visible cells the obstacle may enter during its turn, which enables the planner to reason about which navigation actions may result in collision. This belief tracking method over-approximates the possible obstacle locations and guarantees the obstacle is contained within the region represented by the belief. meaning we can guarantee which regions are obstacle-free. Here we can see a scenario without explicit belief tracking. The robot is shown in blue and the dynamic obstacle is shown in orange. The planner has no way of knowing that the dynamic obstacle is not immediately around the corner and can therefore not advance the robot to the next cell. Here we can see the same scenario, but the tracked belief guarantees the obstacle is within the gray region and cannot collide with the robot at the next turn in the game, allowing the robot to advance to the next cell. Here we can see a simulation run of both the action and navigation planners. We can see how the belief updates as the game evolves. Aziz will now explain how we use the planned actions to generate safe locomotion trajectories for the robot.
The low-level face-based planner consists of two layers. The first layer is the keyframe decision maker, which receives an action from the high level and is responsible for selecting a safe next keyframe state. The second layer is the motion planner, which is responsible for generating center of mass and foot swing trajectories. It uses a reduced order model to describe the dynamics of the chassis bipedal robot. The reduced order model that is used is the prismatic inverted pendulum model. Key parameters are center of mass position at apex, center of mass velocity at apex, relative center of mass height at apex, foot stance position, relative lateral distance between center of mass at apex and high-level waypoint, delta y1, relative lateral distance between center of mass at apex and foot, delta y2. We use face-based planning to generate the trajectories. Face-based planning is a keyframe-based non-periodic planning for dynamic locomotion. A keyframe state consists of action states pairing. The action includes a step length, heading angle change, change in stepping height, foot stance, and stopping command. The state consists of center of mass apex velocity and center of mass apex height. For sagittal face-based planning, we start with the current keyframe state. The next keyframe state is assigned based on the step length from the high-level action and apex velocity from the keyframe decision maker. We then forward propagate the current state. We use backward propagation from the next keyframe state. The switch in foot stance occurs when the two trajectories meet. For the lateral face-based plan, we start with the current state and forward propagate until we reach the switching position. We then search for the next lateral foot placement that would yield zero apex velocity at the next apex. The keyframes and face-based planning are used to develop safety criteria for locomotion. Starting with keyframe-based safety criteria for steering walking. Here we show 3 consecutive high-level waypoints. We would like to plan for a trajectory following 3 consecutive keyframe states, blue, green, and yellow, with circle denoting the apex states, stars representing the foot stance positions. At the green keyframe, a heading change is initiated, which introduces a new coordinate reference frame, shown in red. Projecting the apex velocity and foot stance into the new reference frame yields a lateral and sagittal component. In the sagittal face-based plot, we notice that the apex state is no longer aligned with the foot placement, and to avoid the fall, the face state needs to be within the safety region, bounded by the asymptote of the pendulum dynamics. In the lateral face-based, the face state no longer has zero lateral apex velocity. In order to successfully complete the turn and reach the next keyframe state, the face state needs to be within the safety region. Such bound leads to the following safety proposition. For steering walking, the current apex velocity is bounded as shown. The bound depends on heading angle change, omega, the asymptote slope, and delta y2, which is used as a safety indicator. Moving on to a safety criteria for straight walking. A safety criteria for straight walking is based on the fact that switching position is required to stay between consecutive keyframes, which introduces the following inequality for apex velocity for 2 consecutive keyframes. Another consideration for phase-based planning is high-level waypoint tracking to guarantee obstacle avoidance. Some actions might result in deviation from the high-level waypoint. We use delta y1 as a tracking indicator and require it to be bounded to limit lateral oscillation and to switch time between consecutive keyframes. Since the dynamics are high-dimensional and nonlinear, it is difficult to guarantee tracking for non-periodic motion, as the trajectory depends on the current state of the robot, high-level action, and the next keyframe state. To guarantee tracking, we sample different keyframe transition maps. The reduced order model admits an analytical solution as shown. We use this solution to sample different keyframe transitions and inspect their viability. This is an example of keyframe transition sampling. We sample two steering walking transitions with two different heading angle change. For this figure, it is clear that the smaller heading change would allow a wider range of apex velocities and relative lateral foot positions. We use such samplings to build a locomotion keyframe policy. Our locomotion keyframe policy is as follows. For straight walking, the apex velocity is continuous within the allowable ranges, and the step length is fixed. When an obstacle appears in front of the robot will either come to a stop or switch to steering walking. For steering walking, the apex velocity is maintained within the small range. The heading change is fixed, and the step length depends on the steering direction and the foot stance. Here we demonstrate our hierarchical framework by simulating the trajectory for a pick-and-place task on Cassie robots using Drake. In this example, Cassie comes to a stop when the dynamic obstacle appears in front. Then Cassie steers away until it reaches the goal position shown in green. Here is a 2D plot of the resulted plan. In future work, we would like to simulate Cassie in a more cluttered environment, where Cassie interacts with other robots while avoiding multiple dynamic obstacles, with guarantees on safety and task completion. Here, we show Cassie in a warehouse environment. We would like to thank our collaborators as well as our funding agency.